In today's video, we'll use a technique called the substitution rule that will allow us to take integrals that we haven't been able to take up to this point. In general, they are integrals you can think of as if you were taking the derivative, it was something you would use the chain rule with. Up to this point, we haven't been able to tackle those types of situations. And we'll do it by making just a simple substitution. So if we've had things like this, some of these we could rewrite and work with using our power rules, others we could not. These two here, we could rewrite. The one in the middle there, we could distribute the square root of x. The one on the right, we could FOIL out, and then we could handle that. But the 2x squared of x plus 1, we cannot handle with our current methods. After what we do today, we will be able to handle that. So as I said, basically, we use this in a case where chain rule had been applied to the original function. And it might be easiest to see this starting from the bottom. If we have this here, if we have a function inside of a function, we know when we do chain rule, you take the derivative of the outside function, so capital F prime, keep the inside the same, g of x, and multiply by derivative of the inside, g prime of x. Well, what if we had that now in an integral? Now remember, capital F prime is the same as little f. So this is like saying we had a derivative of an outside function, kept the inside the same, and then times derivative of the inside. So this is something where chain rule had occurred. In order to handle this, we will end up doing a substitution. We will let u be g of x. So instead of having little f of g of x, we'll now have little f of u. Now your derivative of u we'll call du, and the derivative of g of x will be g prime of x times the derivative of the inside of that, which will be a dx. So that whole section here will be replaced by a du. Then if we just have a function and a d, then that's something we can use our regular integral rules for. And it's kind of confusing in notation like this, but you'll see once we do a couple examples, it's not too bad. So let's look at this first example. When we see something like this where it looks like chain rule could have been applied when a derivative had been taken, you need to think about what's the inside function. What is in a spot where we normally just see a plain old x? Well, our normal basic function is a square root of x. So the thing inside where there's normally a plain old x is the 1 plus x squared. And that's what we're going to let u equal. Well, then what we'll do is we'll take the derivative of both sides. Derivative of u will be du. The derivative of the right side, the 1 goes away, we'll have 2x, and then we've got to stick a dx at the end. So what we have here is we have all the things we'll substitute. The 2x and the dx will become the du, because that's what du is equal to. And this section here will become square root of u. So if we rewrite the whole thing now, we'll just have square root du. Now this is something that's easy to handle. We can rewrite the square root of u as u to the 1/2. So our antiderivative will be u to the 3/2. We'll put the 2/3 out front. Because this is indefinite, we need to put a plus c. Now the one thing you have to do at the end is remember to re-sub back in. We didn't really have u in our original problem. Our u is really 1 plus x squared. So all we have to do at the end is replace our u with that original 1 plus x squared. And this is our indefinite integral. Now if you ever want to check it, you can check it by taking the derivative. This would be a chain rule case. 3/2 times 2/3 would just be 1. We'll keep the inside the same, and it's now raised to 1 less than that, which would be 1/2. times the derivative of the inside, which would be 2x, and the c would go away. Well, this is just 2x squared of 1 plus x squared, which is the same as what we started with. So again, you want to use this method, this U substitution, if you have a case where it looks like chain rule might have been applied if you were to take the derivative. And it's up to you if you want to do the check at the end by taking the derivative. That's your choice. Let's look at another example. We need to decide what's the function inside of a function. What do we have where there's normally a plain old x? Well, we normally have cos x. So in its spot, we have x to the fourth plus 2. So we'll let u equal x to the fourth plus 2. We'll take the derivative of both sides. We'll have du equals 4x cubed dx. Well, now we have a problem. We don't have 4x cubed dx. We have 1x cubed dx. So we need to somehow make the right side a 1x cubed dx. And to do that, we can multiply both sides by 1/4. So we'll end up getting 1/4 du equals x cubed dx. So sometimes you might have to make a slight adjustment in your derivative line there by just multiplying both sides by some constant. Notice now what we have is these two together. Those are going to become 1/4 du. Okay, so again, it might not always just be a plain old du. You might have a constant. And this part is going to become cos u. So we'll go ahead, we'll set up our antiderivative. We'll have 1/4 cos u du. Antiderivative of cos is just sine, so we'll have 1/4 sine u. Don't forget the plus c on the end. And then we need to re-sub in for u what it was originally. So we'll have 1/4 sine of x to the fourth plus 2 plus c. If we did our derivative of sine is cos. Keep the x to the fourth plus 2 the same. Derivative of x to the fourth plus 2 would be 4x cubed, and the 4x cubed times the 1/4 out front would give us just the plain old x cubed that we had originally. We saw a square root of x example before. So we know that square root of x is a normal function we see with a plain old x, meaning our u must be 2x plus 1. That means du would just be equal to 2 dx. Well, again, notice we don't have a 2 dx. We just have a dx. So we need to multiply both sides here by 1/2. That'll give us that 1/2 times du is equal to dx. So our dx is now going to be replaced with 1/2 du, and our square root of 2x plus 1 is going to be replaced with square root of u. So we'll have the integral. We'll put the 1/2 out front. We'll have u to the 1/2, and we'll have du. U to the 1/2 will become u to the 3/2. We'll have to multiply out front by the reciprocal, so by 2/3. When you do 2/3 times 1/2, you'll get 2/6, which is just 1/3. And then we'll have a plus c on the end. Replace your u with what it was originally, and we'll have 1/3 2x plus 1 to the 3/2 plus c. And we'll do one more just checking, just to show you that it checks out with differentiation. 3/2 times 1/3 would give you 1/2. This will be 2x plus 1 now to the 1/2 times the derivative of the inside, which is 2, and then the c goes away. Well, the 2 times 1/2 will just give you 2x plus 1 to the 1/2, which is the same as what we started with, so that checks out. So in this one, again, we're used to having a plain old square root of x. Well, we have square root of 1 minus 4x squared, so we're going to let u equal 1 minus 4x squared. Take the derivative of both sides, we'll get du equals negative 8x dx. Now, it might be helpful to think of this as the integral of 1 over square root of 1 minus 4x squared times x dx. That makes it a little easier to see that we're trying to get an x dx. Well, we have negative 8 dx, meaning we need to multiply both sides by negative 1/8. That will leave us with negative 1/8 du equals x dx. And now it matches up. And more often than not, you will have to multiply both sides by some constant. It won't always work out super neat. So this is going to get replaced with our negative 1/8 du, whereas this will get replaced with 1 over square root of u. So I'll put my negative 1/8 in the front. 1 over square root of u can be written as u to the negative 1/2, and then we'll have our du. U to the negative 1/2 will become u to the positive 1/2. The reciprocal of that is 2. 2 times negative 1/8 is negative 2/8, which is negative 1/4. And we need to make sure we have our plus c on the end. And we'll just replace our u with what it was originally, which was a 1 minus 4x squared to the 1/2 plus c. Next example, we'll see e to the 5x dx. The base function we're usually seeing is e to the x. So that means the 5x must be our u, because that's where there's normally a plain old x, meaning du would equal 5 dx. Well, notice our leftover stuff is just dx. So we'll have to multiply both sides by 1/5, meaning 1/5 du will equal dx. So this will get replaced with e to the u, and the dx will get replaced with 1/5 du. Now, students often ask, how do you look to see what the extra stuff is? Well, you should know what your u is, and then you should have your base function, like an e raised to something, or a cos, or a sine of something, or we saw a square root of something. That part stays. Any of the leftover stuff is what you're trying to get the du, or some constant with du, to be. So this will be 1/5 e to the u du. Derivative of e to the u is just e to the u, so we'll just have 1/5 e to the u plus c. And we've just got to replace our u, so we'll have 1/5 e to the 5x plus c. This one's easy to check. E to the 5x would be e to the 5x times the derivative of 5x, which is 5, and the 5 and 1/5 would multiply to 1, giving us what we had to start. All right, we're going to look at a more complicated example now. Hopefully from looking at this, you should be able to spot quickly that we need our u to be 1 plus x squared. The reason we know that is we're used to having just a square root of x. That's our plain old simple function. So we'll have du equals 2x dx. Well, we know this is going to be u to the 1/2. We don't have a 2 at all, so we're going to have to multiply both sides by 1/2. We'll get 1/2 du equals x dx. Well, let's think of this as x times x to the 4th. The x and the dx we know is going to be 1/2 du. But we have a problem. We still have x to the 4th left over. Well, Off to the side, keep in mind x to the fourth we could be kind of clever with. That's the same as saying x squared squared. We need to think, can we write x squared in terms of u? Well, we know u is equal to 1 plus x squared. If you subtract 1 from both sides, you get u minus 1 equals x squared. So x to the fourth can actually be replaced with u minus 1 squared. And this is very difficult. These are the most challenging ones we'll see. And basically, you'll know to look for this if when you take your derivative, you have x's left over, or you have an x to a power that's greater than what your derivative is. So if we neaten this up now, we've got a u to the 1/2. We've got this 1/2 out front. We've got u to the minus 1 squared. And then we've got our du. Well, let's FOIL out the u to the minus 1 squared. So this will be the integral of 1/2 u to the 1/2 times u squared minus 2u plus 1 du. And again, that's just FOILing out the u minus 1. If you can't see that, you can FOIL it off to the side. We're going to distribute through our 1/2 u to the 1/2. So we'll get 1/2 u to the 5/2, because a half and 2 gives you 2.5, which is 5/2. We'll have negative u to the 3/2, because 1.5 gives you 3/2. And we'll have plus 1/2 u to the 1/2. And then our du. We'll go ahead and take our antiderivative. We'll now have u to the 7/2. That needs to be multiplied out front by 2/7, which would give us 2/14. We'll have u to the 5/2. Out front we'll have negative 2/5. And we'll have u to the 3/2. Out front we'll multiply by 2/3, which will give us 1/6. And then we've got our plus c on the end. And it looks messy, but we're just about there. The last thing we have to do is use the 1 plus x squared that we had originally. So we'll have 2 over 14 equals 1 plus x squared to the 7/2 minus 2/5 times 1 plus x squared to the 5/2 plus 1/6 times 1 plus x squared to the 3/2 plus c. And that is our final answer. So we'll look at a couple more examples. Hopefully at looking at this, you recognize we normally have a plain old x raised to the 5th. Well, now we have x cubed plus 8 raised to the 5th. So that wants to be our u, which means du would have to be 3x squared dx. Well, we have an x squared and a dx. We don't have the 3, so we need to multiply both sides by 1/3. Giving us that 1/3 du is equal to x squared dx. So the x squared and the dx will get replaced with 1/3 du, and then this will become u to the 5th. So altogether, we'll have the 1/3 out front, we'll have u to the 5th, and we'll have du. Well, this will become u to the 6th when we take the antiderivative. Its reciprocal is 1/6. 1/6 times 1/3 is 1/18. And we need to remember to have the plus c on the end. And to finish it off, we'll just replace u with what we said it was equal to before. So we'll have 1/18 x cubed plus 8 all to the 6th plus c. Looking at this quick, hopefully you recognize that normally we work with a sine x. So the thing that's where the x normally is the e to the x. We'll let u equal e to the x, meaning du is equal to e to the x dx. Well, notice we have exactly that in this case. We have an e to the x and a dx left over. That'll be our du, meaning this will end up being sine of u. So we'll just have sine u du. Antiderivative of sine u is just a negative cos. So we'll have negative cos u plus c. And we just have to replace our u with what we had, which was e to the x plus c. So we have negative cos x e to the x plus c. And our last example for today, this one's a little tricky to recognize. Think of this as like x times 1 over x squared plus 1. We're going to let the x squared plus 1 equal u. That means that du is equal to 2x dx. Well, we've got the x and the dx. We just need to multiply 1/2 on both sides, so we get 1/2 du equals x dx. So our x and our dx will get replaced with 1/2 du. This part here, we have 1 over x squared plus 1. Well, that's really just 1 over u. So our integral is going to be 1/2 times 1 over u du. Sometimes it's tricky to recognize, but we need to remember when we just had like a 1 over x, or in this case a 1 over u, that's our natural log. When we take natural log, we have to remember to do our absolute value. So we'll have 1/2 natural log of the absolute value of u plus c. Now we'll replace u with what it was equal to, x squared plus 1. So we'll have 1/2 natural log absolute value of x squared plus 1 plus c. Now, because x squared plus 1 always has to be positive, because when you square something it's positive and then we're adding 1, after you plug in the x squared plus 1, technically you could remove the absolute value bars because it'll always be positive, so it would be the exact same thing. That's all for today's video. We'll see you next class period.